Hello, everybody. In today's lesson, I'm going to talk to you about which physics principle is used to describe the motion of a charged particle in a uniform magnetic field. And then we'll use our understanding of this to uh, explain how a device called a mass spectrometer works, and to also talk about what you see in the background of the PowerPoint presentation here, which is an image of the northern or the southern lights. Here are the learning outcomes as identified from the Physics 30 program of study. So we're going to, 1, explain qualitatively and quantitatively how a uniform magnetic field affects a moving electric charge using the relationships among charge, motion, field direction, and strength when motion and field directions are mutually perpendicular. And 2, explain quantitatively how uniform magnetic and electric fields affect a moving electric charge using the relationships among charge, motion, field direction, and strength when motion and field directions are, once again, mutually perpendicular. Okay, let's start off with this. So in this diagram here, I have a negatively charged particle that is approaching a magnetic field. And in this scenario, the magnetic field, which we can represent with the variable B, is directed into the page. That's what those little X symbols stand for in three-dimensional vector notation. Now, what I want to do is I just want to draw a vector that represents the actual velocity of the charged particle just as it's entering this field here. So I'll draw a little dot to represent the point where it's just entering the field. Now, when it just enters the field, the velocity at this one instant in time right here would just be pointing directly towards the right. Now, what I want to do is I want to apply the third hand rule to figure out what direction the magnetic deflecting force would be acting on this charged particle at this point. So the way we would use the third hand rule is, first of all, you need to pick which hand to use. Now, in this case right here, you have a negatively charged particle. So negatively charged particle tells you that you need to use your left hand. Okay, so we're going to use our left hand. Now, the velocity of the particle is going to be represented by your thumb. And the magnetic field is going to be represented by your fingers. Now, the important thing is that when you use the third hand rule, you need to try to keep your thumb and your fingers as perpendicular to each other as possible. Because again, the idea is you're using your hand to represent a three-dimensional grid where like your thumb would point, for example, in the X direction, your fingers maybe the Y direction, and your open palm would face like the Z direction. Now, in this case right here, if you take your thumb and you point it towards the right side of the page, and then you direct your fingers so that they are pointing into the page, the direction of the magnetic deflecting force in this charged particle, just when it enters the field, would be towards the bottom of the page. Okay, so you have Fm right here, magnetic deflecting force. Now, anytime you have, this goes back to physics 20, anytime you have like a particle where it's moving in one direction and there is a net force acting on the particle or the object that is perpendicular to it, that is a condition for circular motion. So what's going to happen right here is the magnetic deflecting force is going to try to change the velocity of the particle. Now, it'll take some time to do that. So it wants to make the charged particle move in a direction that's downwards. It's just going to take a quarter of a revolution of a circle to do that. So once we get to this part of the circle, well, my velocity would then be directed towards the bottom of the page. Now, if you apply the hand rule again, so if you take your thumb and you point it towards the bottom of the page, your fingers into the page, then you would have the magnetic deflecting force that now points towards the left side. So you have Fm. So what this magnetic deflecting force wants to do is it wants to change the velocity of the particle, so it's going to point towards the left. Once again, it takes a quarter of a revolution for that to happen. So at the very bottom of the circle right here, your velocity be pointing towards the left. So if you take your thumb, point it towards the left, your fingers point into the page, then your magnetic deflecting force, Fm, would then point towards the top of the page. So what you can see right here is that all of these force vectors point towards the center of this circle right here, which means that the magnetic deflecting force, when you have a charged particle entering a magnetic field, is a centripetal force. It's center seeking. It seeks the center of the actual circle. That's just a picture of the actual vectors, which I've already done, so just ignore that. So yeah, the magnetic force acts as a centripetal force, and in terms of which physics principle is used to describe the motion of a charged particle in the magnetic field, a uniform magnetic field anyways, it is the circular motion physics principle. All right, so the majority of this lesson is going to be applying this to a device called a mass spectrometer. Now, a mass spectrometer has 4 different parts to it. And we're going to go through each of these parts or stages one step at a time. So you have an ion source, an accelerator, a velocity selector, and then something called a spectrometer. Now, first things first, though, just want to clarify the function of what a mass spectrometer is. The point of a mass spectrometer is it takes charged particles and it separates them based on different masses. So I have no idea why it looks like there's water on the screen there, but let's just ignore it. Okay, so we have isotopes of uranium. So we'll take uranium-235 and 239. Now, I just want to clarify the way that you actually interpret this. So if you have an isotope, I guess we could call this isotope notation. Okay, this number 235 right here, this represents the number of nucleons. Now, what nucleons are the subatomic particles you find in the nucleus. So that would be your protons and your neutrons. Okay, now, if you check the actual periodic table of elements, I believe that uranium has an atomic mass of 92, which means it has 92 protons. So if uranium-235 has 235 nucleons, where 92 of them are protons, that would tell you that you have 143 neutrons. Okay, now, if you compared a couple different isotopes of uranium, so one of them is uranium-235 and one of them is uranium-239, both uranium-235 and 239 have the same number of protons. They're the same element. They're both uranium. The difference between uranium-235 and 239 is that 239 has 4 more neutrons compared to uranium-235. Now, what you'd want a mass spectrometer to do is, for example, you might dig up a sample of uranium. Not that I know where you'd actually find uranium, but let's say you actually do dig up a sample of uranium. The sample of uranium would consist of a bunch of different isotopes of uranium. Now, there's only a certain type of uranium that we actually want, though. It's the 235. The reason we want the uranium-235 is uranium-235 is an isotope that can undergo nuclear fission, which is a source of energy for us, a source of nuclear energy. Uranium-235 will undergo nuclear fission. Uranium-235 will not. Okay, so let's go through the different stages of this chamber here, starting with the ion source. Okay, so we have our sample of uranium, and again, the sample of uranium has like a bunch of different isotopes of uranium in it. So what we would do is we heat up the sample, and we do this for a couple of reasons. One is when you heat up the sample, you can actually take the sample and you can break it into a bunch of small pieces, but make it a bit easier to deal with. And then two is you ionize each fragment. Now, when you ionize the fragments, what happens is you provide enough energy to the actual atom where you cause some of the outer electrons to go away. So, for example, you might make one electron go away, in which case you'd have like a singly ionized isotope. You might make two of them go away, which would be a doubly ionized isotope. Three of them go away, you'd have like a triply ionized isotope. In any of these situations right here, you'd be losing electrons, which would result in having a net positive charge on your actual isotope. So the important thing right here is by removing some electrons, you actually now give the fragment a charge. This is important because once you can get a charged particle or a charged object, we can now have a magnetic field influence it and an electric field, which we'll get into a little bit later. All right, stage 2 is an accelerator. Now, all we want to do right here is in the first stage where we have an ion source, the fragments, the little pieces we broke the uranium sample into, they wouldn't have any speed. So what an accelerator is going to do is it's just going to give these guys some kinetic energy. Now, if you want to figure out what the actual speed of these fragments are like going into the next chamber, we could apply the conservation of energy principle. So let's say, for example, we have like a singly ionized particle, so that'd just be have a net charge of +1. Now, an accelerator is just a bunch of parallel plates. So you'd have like, for example, like here's one parallel plate with a little hole in it. Here's another little parallel plate with a hole in it. Okay, so this guy would enter, and this side would be positive, and then this side would be negative because we want to attract the positively charged particle to the other side of the plate. So we could say that, for example, this right here is state 1, and we could say this right here is state 2. So if you applied conservation of energy, this would look like your mechanical energy at state 1 is equal to the mechanical energy at state 2. Mechanical energy is the sum of kinetic and potential energy. Sum of kinetic and potential energy. Now, excuse me, identifying where you have kinetic and potential energy, I would draw like an equivalent gravitational situation. So basically, this would be the same as you're taking an object, you have a hole in the ceiling, and you're just letting go of the object. So at state 1, you would have no kinetic energy, but you'd have all potential energy. And at state 2, it's like you're just about to hit the ground, so then you'd have no potential energy, you'd have all kinetic energy. Now, if I expand this equation right here, EP would become the charge magnitude multiplied by the voltage at state 1, which would actually just be the potential difference across the parallel plates. And that would be equal to 1/2 m V2 squared. If I manipulate this for V2, this would then be 2 times the charge magnitude times the voltage at state 1, or delta V, the potential difference across the plates. Divide this by m, and you get an equation for V2. Now, I want to point out a little bit of a complication at this stage right here. So the problem with this right here is when we heat the actual fragments up, we don't know what charge the fragments are actually going to have. So this Q value right here, some of these fragments might be singly ionized, some of these fragments might be doubly ionized, some of them might be triply ionized. Depending on which of those cases the fragment would fall into, you're going to get different speed values. The other thing we don't know is the mass, because there's different isotopes of uranium. Some of them have more neutrons than the other. So what you could have right here is you could actually get a bunch of fragments, because they have different charge and mass, that are going to be moving at different speeds once they exit the accelerator. Now, I'll make up some fake numbers right here. Let's say that, for example, one of these fragments exit with the speed of like 1.00 times 10 to the 6 meters per second. One of them is 2.00 times 10 to the 6 meters per second. Some of them would be 3.00, 10 to the 6 meters per second. There's no way these numbers are actually this clean, but I just want to illustrate the point that because you have different charge and mass values for like your isotopes, you're going to have different speeds at this point. So lots of particles with different speeds. Okay, on to the next chamber. So we have something called a velocity selector. Okay, I've already illustrated this point on the previous page. So your ions coming from the accelerator are going to have different charges and different masses depending on whether they're singly, doubly, triply ionized, and different masses depending on which isotope we're actually looking at. Now, what the velocity selector does specifically is we're going to be very choosy about what kind of particle we want to go through. So if I go back to this previous slide right here, I might only want to let particles with a speed of 3.00 times 10 to the 6 meters per second pass through. Now, we'll kind of talk about how we can do that in a second, but we need to first of all establish what the inside of a velocity selector looks like. The inside of a velocity selector actually has two kinds of fields inside. It has both an electric field and it has a magnetic field. Okay, so this is kind of like the inside of like what a velocity selector would look like. Now, because the picture is in 3 dimensions, I'm just going to clarify like a little tiny grid right here just to so we don't get like tremendously confused with the actual picture. Okay, let's say that towards the top of the page is the y direction. Let's say towards the right side of the page is the x direction. And then this line right here, okay, z, that's going to represent, and I'll draw a little circle to dot right here, that would represent coming out of the actual page. Okay, so if you look at this picture right here, what I can see is, I don't know why it says E right here, because this would be a positively charged particle. So let's just change that to a plus. Okay, so in this case right here, this charged particle would have a velocity that is pointing in the, this is supposed to be an arrow, by the way, a velocity that's pointing along that z-axis. Now, as you can see right here, what I have is I have a couple of objects that produce the two fields I want. So first of all, I have some parallel plates. So in this case right here, the top plate is going to be negative, the bottom plate is going to be positive. If you want to know what direction the electric field is between those plates, you just put a positive test charge there. If you put a positive test charge anywhere in that region between the plates, the positive test charge would repel from the bottom plate and attract to the top plate. So if I drew the electric field lines to represent this, well, the electric field lines are roughly uniform between parallel plates, and they'd be directed along the y-axis towards the top of the page. Now, the magnetic field is going to come from those two barb magnets that you see there. And again, the way you draw magnetic field lines between barb magnets is they must come out of the North Pole and go into the South Pole. So in this case right here, my magnetic field would be towards the right. Now, in the region directly between the magnets, we can make, an approximation that the field is roughly uniform. As you get away from the actual magnets, the field will not be uniform. Same thing with the parallel plates. Once you get outside of the region, the field is no longer uniform. Okay, now, what I can see right here is that I have fields that are crossed. I have an electric field that points towards the right along the x-axis, and I have an electric field that is pointing up towards the y-axis, and a magnetic field that is pointing towards the right along the x-axis. Those fields are crossed, and they're both perpendicular to each other. Now, I'm going to use a free body diagram to identify to derive an equation that I can use to deal with particles when they're in a velocity selector. Now, the idea right here is that you want to adjust both the electric and the magnetic field so that that charged particle would exit through a very tiny hole on the opposite side of the selector. So some particles, when they come in, so I'll do like a side view perspective of this. Some particles, when they come in, would drop down, okay? Some particles, when they come in, would probably go too high. What I want these particles to go through undeflected. So what I'm going to have to do is I'm going to have to adjust the electric and magnetic fields to do this. Okay, but let's look at a free body diagram to kind of get an equation that's going to relate the speed of these particles to both the electric and magnetic field. Okay, so here's my charged particle. Now, it is a positively charged particle, so a positively charged particle would just move in the same direction as the electric field. So that's going to be directed towards the top negative plate, which is in the y direction. Now, for the magnetic deflecting force, you'd need to use the third hand rule to do this. Now, in this situation, we're dealing with a positively charged particle. So a positively charged particle means use your right hand. Okay, now, from the perspective shown right here, using your right hand, you take your thumb to represent the velocities. Your thumb would point into the page. Your fingers would then point towards the right side of the page, and then your open palm would then face towards the bottom of the page. So that'd be like the negative y direction there. And that's why you can see in the free body diagram that the magnetic deflecting force is pointing straight down. Now, what I want in a velocity selector is I want those particles to go through undeflected, which means that I need both the electric and the magnetic force to be equal and opposite for this to happen. Okay, so let's expand this equation of motion here. Okay, if we assume up is the positive direction, then Fe would be positive, Fm would be negative, so you have Fe minus Fm is equal to 0. If you add Fm to both sides of the equation, you get Fe is equal to Fm. Now, we can expand both sides of the equation right here. So the magnitude of the electric force would just be the charge magnitude times the electric field strength. And the magnetic deflecting force magnitude for a charged particle in the magnetic field would be QVB sine theta. Now, we can simplify this equation a little bit right here. So first of all, the two charges cancel off. The second thing is theta represents the direction between the velocity of the particle and between the magnetic field. So in this case right here, the velocity of the particle is directed straight into the page, and the magnetic field is directed towards the right side of the page. So they are perpendicular to each other. If they are perpendicular, it means theta is 90 degrees. Sine of 90 is just equal to 1. So if you manipulate this equation for V now, you would then get V is equal to E divided by B. So let's say again that like there's only one kind of particle that you actually want to go through. That's like the one with the speed of like 3.00 times 10 to the 6 meters per second. So what you'd need to do is you'd need to adjust the electric and magnetic field strength until you can actually get that numerical value. Then we know that the only kind of particle that's going to pass through are particles with that exact speed. And that's why it's called a velocity selector, or being very selective about what kind of particles we want to go through and what we want their velocity to actually be. Okay, stage 4, we're now into the detection chamber. Now, the only kind of field that would be in this region right here would just be a magnetic field, and that is it. So in the picture right here, we can actually figure out what the direction of the magnetic field is. So when the particle just enters the actual field, my velocity would be towards the right side of the page, and your deflecting magnetic force would be pointing towards the center of the circle. Okay, so once again, you can use a third hand rule, except this time you need to try to figure out what directions your fingers have to point. So you take your right hand, because we're talking about a particle that's lost some electrons, so it's positive. Your thumb points towards the right side of the page, and your open palm would then face towards the bottom of the page. Now, if you orient your hand correctly when you do this, your fingers should be pointing out of the page at you. So in this case right here, the actual direction of the magnetic field will be out of the page, will be represented by a bunch of little dots. And if we wanted to show that the magnetic field is uniform, we just evenly space them. So that'd be your magnetic field direction. And as identified before, if a charged particle enters a uniform magnetic field, then it's going to deflect in a circular path. Now, these charged particles will deflect in a semicircle, and then after they deflect in a semicircle, they're going to hit this plate right here. Okay, this plate is called like a detection plate, and it's like a spot where you would just accumulate a bunch of these isotopes. Now, based on what the radius of the path is, we can figure out what kind of isotope is deflecting in which circle. Now, if you look at the picture right here, it shows you that the heavier isotope has a larger radius of a circle. So that'd be like a big radius right here, R is big. And then this one right here, this smaller circle, would be the lighter isotope. Oops. And I just erased everything. Oh well. Okay. Yeah, so what was I doing? Oh yeah, I was clarifying that this is the lighter isotope. This time I'm going to spell isotope correctly. Okay, now we want to prove that. So what we want to do is we want to prove that the larger radius path is going to be associated with a heavier isotope. And to do this, we're going to again look at a derivation of an equation from a physics principle. Okay, so this time around, we're moving in a circular path. So we do have centripetal acceleration. So I'm going to draw the mass acceleration diagram as well. Now, the only force acting on this right here is a centripetal force, which is the magnetic deflecting force. The magnetic deflecting force is behaving as a centripetal force. According to Newton's second law, whatever direction your net force is, your acceleration has got to be in the exact same direction. So your centripetal acceleration also points towards the center of the circle. Now, we'd write down the circular motion physics principle, starting with sigma Fc is mac. Now, it's not even a sum right here. There is only one centripetal force. It is Fm. Now, just for the sake of convenience, it makes a lot more sense to make down the positive direction here. Okay, so this would be Fm is equal to m, and you just might want to recall for circular motion, there is an equation for your centripetal acceleration magnitude, and that's just equal to v squared divided by r. Now, to expand this a step further, we'd have qvb sine theta. So again, that's the equation for the magnetic deflecting force acting on a moving particle through a magnetic field, and that'd be equal to mv squared over r. Now, part of this equation right here can simplify. If you divided both sides of the equation by v, you could get rid of a v on the left-hand side and like one of the v's on the right-hand side. Now, once again, the direction between the magnetic field and the velocity of the particle is always going to be perpendicular. So, again, going back up to the picture, which I annoyingly erased here, at the very top, that's supposed to be a vector pointing towards the right. So vectors pointing towards the right, and again, your magnetic field would be directed out of the page. They're perpendicular to each other. Okay, now, if I manipulate this equation, I can get an equation that looks like this for my mass. So I have m is equal to r-q-b divided by v. Now, the only thing I want to point out right here is that, there is a direct relationship between m and r, which means that if a charged particle has a larger mass, it's a heavier isotope, then it's going to be having a larger radius of deflection. So again, let's going back to that issue of you dig up the sample of uranium, you've got uranium-235 and you got 239. The only sample I want is the 235 because that's the one that'll undergo nuclear fission. So you'd use this apparatus right here to separate the two of them, and the uranium-235 would then be collecting on the detection plate with the smaller radius. So you'd be looking at this right here to get your uranium-235. Okay? Mass spectrometer is like a really, really good device to like analyze because there's so many physics principles involved in them. The accelerator chamber, you either have like the conservation of energy or uniformly accelerated motion physics principle that describes a motion. The velocity selector, you've got balance forces, and the spectrometer part of the chamber, you have circular motion. So there's like 3 different physics principles you need to like properly understand to describe how a mass spectrometer works. Okay, one more thing, and we're back to a slide that looks like water is all over the screen. I think it's because I have, not that you guys actually care about this, but I have like dual monitors set up right now, and like for some reason it doesn't seem to like me splitting the display over 2 screens, so it freaks out at me a little bit. What happens if I go back and come back here? No, it's still the same thing. Okay, so we're just going to have to bear with it. Okay. Van Allen radiation belt. This is a really fancy word for the northern or the southern lights, which is going to be what I want to just try to explain here. And this is actually really, really complicated to properly explain. So I'll do my best, but it's probably going to end up being like a terrible explanation as to like how this actually works. Okay, well, let's ignore this first bullet point right now because it's not going to make any sense at this point. Okay, and then got a picture here. Okay, I think I'll explain the first point to start off with. Okay, so the sun produces a bunch of charged particles that are called solar flares, and these solar flares like go through empty space. So maybe I could just like draw this right here. So let's see if I can get yellow. Okay, so let's draw the sun. Okay, and the sun sends a bunch of these charged particles, which we call solar flares, towards the Earth. Now, if we didn't have an atmosphere, these charged particles, I think, would actually be like pretty fatal to us. So, like, thankfully, you do have a magnetic field to like protect us against this, and we also have an atmosphere as well. Uh, okay, so first thing I'll explain is like the color that's associated with like the actual northern lights, and we'll talk about that first bullet point about like what kind of an angle relative to the Earth's magnetic field the charged particle needs to uh, approach in order to actually get the in order to actually produce the northern lights. So the idea is pretty much this in terms of the color. So what these charged particles do is these charged particles, they enter the Earth's atmosphere, or actually not yet. They enter the Earth's magnetic field. I'm going to draw with a different color right here because we're not going to be able to see this, although for some reason it's not letting me change color now. Oh, I see. The pen's right there. That's why. Okay. Okay. So let's say these charged particles approach, they approach, they approach, they approach. Now, when they hit a magnetic field line, what they do is, we'll talk about like why they spiral in a second, but basically they hit one of these magnetic field lines and they start spiraling around them. Okay, spiral, spiral, they spiral. Okay, and eventually they're going to hit the Earth's atmosphere. Now, when they hit the Earth's atmosphere, what they do is these charged particles transfer some of their energy to whatever molecules make up our atmosphere. So that could be like nitrogen or oxygen. Now, what ends up happening is when they transfer some of their energy to these atmospheric gases, it causes them to glow. There's a bit more of an explanation as to like why they glow, where we'd have to talk about like electrons jumping between states, between energy levels or states in the actual atmospheric gas, the atoms of them. But that's something we'll talk about like later in the modern physics unit in terms of like how we actually get visible light. For the time being, I think it's just safe to say that if you have a high energy particle, it hits gases in the atmosphere, it transfers energy, and it makes them glow. Okay, now we need to talk about this second little bullet point here. So I'm going to go to this next slide, and I'm going to attempt to explain this. But again, this is really hard to properly explain. Okay, so let's say the Earth's magnetic field is directed. I'm going to draw a bunch of X's right here just to represent it. So we'll have an X. We'll do three of them in a row. Three rows of three. That's 9, by the way, if you want to do the complicated math on that. Okay, now I'm going to establish a grid here. So let's say this, that we have, here's my Cartesian grid. We'll say this is Y. We'll say this is X. And we'll say this right here is Z. Okay, now I'm just going to change the ink color here. Okay, I want these magnetic field lines to be directed along the Z-axis. Okay, so let's actually change the color of the Z-axis to purple. Okay, so I'm going to draw a little line right here that what this line is telling me is telling me that the magnetic field right here is just along the z-axis. Okay, along the z-axis. Along the z-axis, along the z-axis. This is going to be important when I draw a picture just in a moment here. Okay, along the z-axis. Okay, and then B for the magnetic field. Okay, now I'm going to look at a couple different cases right here in terms of like how, like what happens if we approach in a specific manner. Okay, so let's say, for example, that you have a charged particle that approaches along the z-axis. So I'm just going to pick a different color here. So let's pick green. So a charged particle approaching along the z-axis might be like this right here, okay? So that would be V, approaches along the z-axis. Now, in this case right here, the charged particle approaches along the z-axis, and the magnetic field is also along the z-axis. So in this case right here, the angle between the magnetic field and the particle would be 0 degrees. So if a charged particle approached along one of these field lines right here, then nothing would happen, okay? Your motion would be unaffected. Basically, the charged particle would just go along the line. So if it's a solar flare, it would go along the line, and then it would just go back into space. I'll say motion unaffected. Okay, so that's one extreme, is that we approach directly along one of these along the same axis. Okay, now I'm going to draw a second grid here. So we'll say Y, we'll say X, then we have Z again. Okay, and now this time around, let's say that the charged particle approaches in a direction along the x-axis. So maybe it approaches like this right here. Now, in this case, the x-axis and the z-axis, so the charged particle is along the x-axis. The z-axis is perpendicular to the x-axis, so the angle between the direction that the particle is moving and the actual the magnetic field is 90 degrees. Now, what would happen in this situation right here is if this charged particle entered the magnetic field, it would just undergo circular motion. So it would go into the field, it would go in a circle, and then it would just come right back out. Or if it was moving fast enough, it might get stuck in the field. Who knows what could actually happen right here, but it would just undergo circular motion. Okay, now let's go back to this other slide for a second. So what I said right here is what you need is a charged particle to enter the Earth's magnetic field at an angle between 0 and 90. Okay, so it can't be 0 because if it's 0, its motion's not affected. It just comes in and goes out unaffected. 90 degrees would be it just goes in a circle or a semicircle. Again, it goes in and comes straight back out. Okay, so now let's look what happens if we approach at an in-between state. Okay, so I'm going to again draw a little grid here. Okay, so that's the y-axis. This is the x-axis. This is the z-axis. Okay, so let's draw. I'm going to do this in purple, I think, this time. Okay, so we're going to approach at an angle between the two extremes. We're going to approach at an angle that looks something like this right here. Okay, so I'm going to call this V. So it's an angle between the one extreme on the z-axis would be a 0-degree angle, and the other extreme on the x-axis would be a 90-degree angle. Now, I'm going to take this vector and break it into two components. So I'm going to make one component parallel to the z-axis, and one component that is parallel to the x-axis. Okay, so we'll call this one VZ, or I'm going to call it V parallel because it's this component of the vector is parallel to the Earth's magnetic field. And this one right here we're going to call Vx, or V perpendicular because this component is perpendicular to the Earth's magnetic field. Okay, now here's what we have. These two components do a couple of different things. So what this perpendicular component does, so that's going to be this one right here. This one is responsible for making these solar flares move in a circle. Okay, so if they came into the actual magnetic field, they would just move in like a circle like this. Okay. Now, this is where it's difficult to explain. This is where I wish like I could actually do like a proper demonstration in the class. What this Z component right here is going to do is it's going to kind of like take this circle and it's going to like push at it. Now, the analogy I like to use right here is like, think of like having like a slinky that's like nicely compressed together. Like to start off with, your slinky is like there's all like the different lines and they're all like nicely like compressed together right here. Okay. They're all very densely compressed together. Okay. So the X component of this velocity or perpendicular component, that's responsible for making the particle go in a circle. Now, what this Z component or this parallel component is going to do is it's going to like separate the slinky apart. So if you take the slinky and you start to separate it, okay, so instead of like coming back into like where you started, okay, we actually start to get this little spiraling effect that's occurring. So we kind of like start to stretch the circle apart. So what happens is the charged particle, okay, so your solar flare, would enter the Earth's magnetic field, tries to go in a circle, but since there's that one component that's parallel to the magnetic field, it starts to push this circle and spiral it. And eventually what happens is this guy's going to spiral until it finally hits it hits a spot where the Earth's magnetic field is going to collide with the atmospheric gases and be perpendicular to it. That's at the poles, okay? So eventually, like as this thing spirals, it'll eventually get to a point where the actual magnetic field lines are perpendicular to the atmospheric gases. And that's why we see the northern and southern lights at the poles. Anyways, that's a very complicated explanation. Like, I don't know how much like detail you actually need to know about how the northern and southern lights work. There's a challenge problem on a later assignment that deals with this concept of spiraling. So if you understood what I was talking about right here, good. If not, then I mean, look at the slide. I don't blame you. It's confusing. Okay, so I think I actually renamed the assignment. I think I called the assignment Mass Spectrometer Assignment. So that is what you need to complete. It's a hand-in assignment. Thanks for listening. I hope I explained a few things about the mass spectrometer and about the northern and southern lights. Thanks.